Okay. So in the previous experiment of the small signal amplifier, we built this circuit. First we built it on multisim, and then we built it on the actual device itself, and we looked at the amplification, and we saw that this is the black color line is the input signal, the red color line is the output signal. And we saw the frequency did not change from the input and the output, but the amplification was it was amplified. So in this case, we have an input of. Let me make sure that I'm taking the output at the right place. Yeah. So it's like a 4-volt output and 1.5 volts input. But if you look at the current, let me do that real quickly. It's sorry, it's 1.27 exponent. That's milli, right? So minus divided by 11.7 micro. So that's milli micro minus 16, minus 6. And so that's an amplification factor of about 108. So that's the calculation that I just did. Okay. So the input to the output, I get about 108 or so amplification, which is like a beta if you want to think of it that way. The problem with this particular amplifier is that you notice that half of the waveform gets cut off. So it's not desirable in that sense. Okay? So it only conducts during this positive going waveform. So there is nothing that's happening during the negative going waveform. And you can see why that happens. That's because this transistor here is an NPN transistor. So the transistor conducts only during the positive going waveform. It does not conduct during the negative going waveform. When it's not forward biased during the negative going waveform. So that's a serious disadvantage, even though we can use this as a signal amplifier, especially if you're using this as a very small signal amplifier where, it's not like an audio signal where you're that concerned about the fidelity of the sound. This would work fine. For example, if you're using this for a signal amplifier of a thermistor or a thermocouple, this is perfect. You can use this. This will work. Okay, as long as this 1 millivolt and 4 volts and 1 milliamp is sufficient. But realize that the input is 11 microamps. That's a really, really small current that you're putting into this device. And you're getting one hefty output out of this. Okay. So again, for like instrumentation, like a thermocouple, that type of thing, some kind of sensor, like a proximity sensor, all of those things, this will work fine. Okay. I mean, I'd have a signal sensor, a signal output out here, but does not have to be a signal output. It could be some sensor, for example. So it works fine for that type of application. But obviously enough, it is not good enough if you want audio amplification. So I have another circuit that was built, and that's this one. And it has a few more features to it. And this is a very classic common emitter amplifier. So that's a small signal amplifier, and that's a common emitter amplifier. Okay. So it is a little bit more complicated, but it does a really good job of signal amplification. So We get the oscilloscope for this one. So the oscilloscope output, we'll pause that, and we bring that back out here. So the blue color line is the output, which is this one here, which is represented here, and the red color line is the input, which is this line here, and that's represented here on the oscilloscope. And you see the signal, it's a really, really small signal. What is it? About peak to peak input voltage is about 11 millivolts, and I'm getting peak to peak output about 572 millivolts. But even more interesting than that is the input current. Remember, bipolar transistors are current amplification. This is a current amplification circuit. When we talk about MOSFETs, we'll get more into this, but bipolar transistors are current devices. I'm going to digress just a little bit here, since we are talking about current and MOSFETs. I wanted to look at our syllabus. So we've done this part, we have done this one, we've done the small signal amplifier, and so if you may recall, just a few minutes ago I mentioned MOSFET devices, so that's this lesson actually. And then lesson 13 is this device. Right now what I'm doing is lesson 14. I'll come back to this, but I thought since we were talking about amplifiers, and like a small signal amplifier right here, I thought it would be just as well to go into a single stage amplifier and the common emitter circuit, just looking at that instead of going into another device and jumping back and forth. So that's the reason why I'm talking about this other amplifier, because we had covered this one up here. So instead of going into another device, we'll do this common emitter amplifier first, and then we will go into the MOS field effect devices. And interestingly, once we have done, I should be able to get this presentation done within the next couple of days. Once we have this MOSFET devices done, we will be ready for the second exam in this class. Now, when that second exam will be, or the format of it, I don't know at this point. Certainly, I don't know the date, but I'm relatively sure that it's going to be on Canvas. So it'll be a Canvas-based exam. I may also put a quiz in here somewhere, just so that we know how to do the exams and quizzes. Okay, so a little digression there. I just wanted to make sure that we are on the same page. Okay, so we're talking about the common single stage amplifier, and this actually is a pretty standard circuit. It's called the common emitter single stage amplifier. And why it's called single stage is that there's only one transistor. So if they had another transistor cascaded next to it, then it would be a two-stage amplifier. All that would do is to increase these values and make it a more efficient amplifier. Obviously, in this situation, will not be a very suitable amplifier, especially if you're talking about high quality audio and things like that. But for all practical purposes, this is like a perfect amplifier. And you'll notice that in this case, I just did the calculations. I have about, if you're talking about the current, I have about an amplification of about 131. Okay, so I got those from this number here, the peak-to-peak current values. You can take peak-to-peak or RMS, doesn't matter, it's the same mathematical formula. So from 1.9 microamps, I'm getting 260 microamps output. And with 11 millivolts, I'm getting 572, which is about 52 times amplification. Let me make sure that that number that I just told you is correct. So it's 572 divided by 11. Yeah, 52. So the amplification, the voltage amplification is 52, and the current amplification is 131. So this is a really good amplifier for all practical purposes. And you'll notice that I don't have that problem of cutting off one of the waveforms, because that was a problem with the previous circuit, is that I cut off one of the parts of the waveform, right? This top part, you notice that when the input went down, this shut off. I don't have that with this circuit. Okay. And part of the reason for that is why this is conducting in both sides is that I have an input. Where is the power source? Oh. Turn that around. Oh, here, this power source here, this 10 volts here, that forward biases this transistor also. So there are two forward biasing sources for this transistor. I have this, but it is fed through a 10 kilo ohm resistor, so it's not like it forward bias it all the time. But then I have a forward bias from here also. So the combination of the two, this forward bias and this forward bias, is what makes it conduct during both waveforms. Now, this transistor would have conducted during the positive going waveform anyway because of this, but during the negative going waveform, it has this part to make it conduct. Okay. So there are two power supplies in this circuit. The first one is this one here, which is, it's a very small power supply, 10 millivolts peak. And then I have 10 volts, which is a pretty hefty power supply. But that's a DC power supply. And I'm getting an AC output from a DC input. Okay. So that covers the small signal single stage amplifiers.